Okay, so I thought we would do some more examples now of finding antiderivatives. We've been doing that quite a bit lately, right? So as an example, so you'll notice that this integral does not have limits of integration on it. So this is not a definite integral, right? We know when this says find all antiderivatives of the function x to the third plus 4x squared, mindful that this right here is our derivative function. What we're trying to figure out is what's the original function, right? And we know from our previous experiences that we can just read these off term by term. And add a vertical shift, okay? But how about this now? Let's make it a little bit more interesting. Suppose that we have this example. Okay, right? So the entire derivative expression is sine cubed times the cosine. Again, I'm gonna write it like this because we know that symbolically this means the same thing. Okay, right? So all of this, that's our derivative function, you know? We're trying to get back to the original function. We want to recover that original function, okay? If notice, maybe you don't, maybe you do. Do you notice, again, that that's a chain rule? Yeah, why? Why is it a chain rule? Yeah, the outside, right, the cosine of x is exactly the derivative of the inside function, okay? But it's missing a little bit, right? It's missing a little bit. If this expression is the result of the chain rule, then this is missing something. What's supposed to be in the front here, right? If that's a 3, what's supposed to be down here? Yes, very good. It's a 4. It's missing a 4. So I'm going to put the 4, I'm going to fix it. I'm going to adjust it. Okay, so I'm going to put the 4 in there, but be careful. The 4 wasn't there to begin with. All right, so I'm going to have to multiply by a 1/4, and I'll compensate on the outside. Okay, so what I've done is I've multiplied by a clever expression of 1. Okay, now I see a perfect chain rule here. Okay, and so all of this then, right, all of this can be found by taking the derivative of the sine of x, I'm sorry, the function sine of x to the 4th power. Take the derivative of that with the chain rule, okay? That 4 will come down in front. It's right here. Subtract 1 from it to get 3, which is right there. And then you're going to multiply by the derivative of the inside, which is the cosine. Don't forget that 1/4 we had out in front, though. And then, of course, we add a vertical shift, okay? Let's check. In case anybody has any doubts, we don't want anybody walking away thinking, what? What happened? Okay, so I'm going to take the derivative of this result. All right, so I'm going to set the 1/4 aside. By the chain rule, the 4 comes down, we subtract 1 from it, and then we multiply by the derivative of the inside. Derivative of the sine is equal to the cosine, and of course the derivative of the constant is equal to 0. And so this just leaves us with what we had at the beginning. Okay, so it checks out. All right, it checks out. So these are the kind of examples I'd like to focus on now in this presentation, okay? When the integrands themselves are compositions, in other words, the results of the chain rule, okay? Before I get into that, let me remind you, we saw earlier, right? We saw earlier the special case of the chain rule. Okay, the special case of the chain rule, which said this, right? If you take the derivative of a function raised to a power, then by the chain rule, that was equal to, you bring the power down in front, subtract 1 from it, and then you multiply it by the derivative of the inside function, like this, okay? Now, the reason I single this out, gang, and the reason we mentioned it before in the previous lectures is the frequency with which these kinds of compositions occur, and therefore their derivatives. So now you want to think about starting on the right-hand side and getting back to the left-hand side. All right, so that's what we're all about, you know, with this business with anti-differentiation. All right, well, here's an example. Let's suppose that we had a little bit of a variation on that last example, okay? So here, notice that we do have a chain rule, right? It does look similar to the special case. What's missing in front? Yes, good. What's missing in front is the 11. So I'm going to multiply by 11 on the inside and 1 over 11 on the outside, okay? Now I've got a perfect chain rule. And so therefore I can go right to the end. Don't forget that 1 over 11. But otherwise, the integrand is the result of taking the derivative of the sine function raised to the 11th power. Okay, and then plus c. What do you think of that? Okay, so essentially, again, what we're looking for is this. I'll make another remark. Okay, what we're interested in okay, this is what we've been doing for a while. Okay, find the antiderivative of this thing. And it's some function plus a vertical shift. But now we want to focus on compositions. So suppose the integrand is not f prime of x, but f prime g of x, okay, times the derivative of that inside function. Okay, that's what we're after now. All right, all of our most of our integrands now are going to be of this form. Okay, they're going to be a little more complicated than what we've seen. What we're on the lookout for are chain rules. Okay, because that's what we're looking at here. Okay. Example. Let's suppose that we had like this. Okay. Now, what do you think, gang? Are we looking at the result of a chain rule? Yeah, it looks like it, right? Notice that the outside function t is almost the derivative of this inside function here, okay? Well, let's see, the derivative of the inside function is 2t. We've got 1t on the outside, we just don't have the 2. First of all, let's write like this. Let's write t squared plus 1 to the 1/2 power times t. All right. Now I know that for this to be a true chain rule, I'm missing a couple of things, right? I'm missing a couple of things. First of all, the outside has to be the derivative of the inside function t squared plus 1, which is 2t, and I only have 1, so I'm going to fix that. I'm going to multiply by 2 right here, and 1/2 on the outside to compensate. All right, so I've multiplied by a clever expression of 1. All right, what do you think about it? Does that make sense? Okay, good. Now, what should be in the front? What's supposed to be in the front, right? Because we said there's a couple things missing. Okay, we've addressed the derivative of the inside, right? But for the outside part, what had to come down in front? So when you subtracted 1 from it, you got a 1/2. Good, 3/2. All right, so I'm going to need a 3/2 here. All right, but to compensate, I'm going to need a 2/3 out in front. Let me put that here. Should have made a little bit more room. Sorry about that, gang. Right, 2/3 times 3/2 is 1. Okay, see how we're making adjustments with constants? And so the overall result is going to be this. 2 over 3 times 1 over 2 times all of that now is your derivative function. Okay, and it's a perfect chain rule. Okay, it's the special case of the chain rule. It's the special case. So this is going to be t squared plus 1 to the 3/2. And of course, then we add a vertical shift. And I'm not doing anything special. I'm not using any techniques. What I'm relying on are our previous experiences. Okay, we have such extensive experience getting taken derivatives of functions. That's all going to come to bear now finding antiderivatives, especially for integrands that are the result of the chain rule. Okay. All right, next example. Let's suppose that we had like this. Okay. Now, notice this is the result of the chain rule, right? Because notice that the 2x is exactly the derivative of the exponent. It's not the special case of the chain rule, right? It's not the special case where we have a function raised to a power, but it is a chain rule. Let me remind you, maybe I'll write it over here in red, recall, right? Recall from our earlier work that the derivative of e to the u of x, a composition, is equal to itself times the derivative of the exponent, okay? And we have exactly that here, okay? And so I can go right to my answer then. This must be equal to e to the x squared plus c. Now again, check it. Don't take my word for it. Take the derivative of this function, okay? The derivative of this expression is going to be, let's see, by our work right here, okay? The derivative of the natural exponential function, it is itself, times the derivative of the exponent, and of course the derivative of a constant is equal to 0. And that's exactly the integrand that we have here, okay? Nothing special was necessary, okay? Example. All right, well, suppose it's this now, all right? Suppose it's this. Now, is this a chain rule? Yeah, it might not look like it right away, huh? But if you notice, gang, what is the derivative of the denominator? Yeah, it's 1, right? The derivative of the denominator is equal to 1, which you have in the numerator, okay? The numerator is exactly the derivative of the denominator. Well, again, remember from our earlier work, right? Remember from our earlier work, we said that the derivative of the logarithm of a function is equal to the reciprocal of that function times the derivative of that function, which I'll just write here because I'm running out of space. So that means here, this is going to be exactly equal to the logarithm of x plus 1 plus c. Okay? Example. Now we don't have an antiderivative for the tangent function because I can't write something over here so that when I take its derivative will lead me right back to the tangent function. Okay. However, I know that I can write the tangent as the sine divided by the cosine. Okay. And then I notice that the derivative of the denominator is minus the sine of x, which is in the numerator. Okay. Gang, that fits this form right here. Right? The numerator is the derivative of the denominator. That came from a logarithm. Right? Now we're off by a little bit, right? The derivative of the cosine function is minus the sine, which I have in the numerator. I just know the minus. So I'm going to multiply by a -1 on the inside and a -1 on the outside. Okay? So now I have the numerator is exactly the derivative of the denominator. Right? So take that -1. And then because of our logarithm rule, for lack of better words, this is going to give you the natural logarithm of the cosine function plus a vertical shift. Okay, check. Take the derivative of your answer. Set the -1 aside. That's the constant multiple rule. Okay, but otherwise, the derivative of the logarithm of the cosine is the reciprocal of the cosine times the derivative of the cosine, which simplifies. Right, minus is positive, sine over the cosine is the tangent, and it checks out. Okay, again, just by using our experiences and what we recall from the chain rule. Okay? All right, how about this? Do we have a chain rule? It looks like it, right? The derivative of this inside function, 1 plus x squared, is 2x, and I've got 1x right there. Maybe I rewrite this like that. Okay, so I've got a function raised to a power. And gang, look at that. The outside is almost the derivative of the inside. I'm just off by a little bit. How much am I off by? Yeah, I'm just off by 2. That's our thing. That's the special case of the chain rule. You know, that thing. So I'm going to multiply by a 2 here, compensate with a 1/2 out in front. All right? Now, for it to be a perfect chain rule, what should be in the front here? In other words, gang, what exponent did I have to bring down in front and then subtract 1 from to get this? What was it? Good, 1/2. So I'm going to bring a 1/2 here, going to multiply by a 1/2, and I'm going to compensate by multiplying by 2 on the outside. Look at the adjustments. I'm just making adjustments with constants. Now listen, hey, don't get cocky. You can make adjustments with constants like that all day long. You can't do that with variables though. All right, you can't do that with variables or variable expressions. Only with constants can you do this. Okay, so now that the integrand is a perfect chain rule, it's the special case, right? I'm going to have this 2 times that 1/2. And then all of this came from taking the derivative of 1 plus x squared to the 1/2 power. And then, of course, a vertical shift. Now, the 2's, of course, will cancel. Now, let's check. All right, let's check. 2 times 1/2, that's the constant multiple. Set the constants aside. The derivative of this by the chain rule, 1/2, 1 plus x squared to the negative 1/2 times 2x. This cancels with this 2 with this 2, and that leaves me with x divided by square root of 1 plus x squared, which was the original integrand. So it checks out. Okay? So there are many integrals, gang. There are many indefinite integrals, right, that don't have limits on them. They're called indefinite integrals that you can actually calculate based on your experiences. You don't need any special techniques. Just be confident in your abilities and the chain rule. Okay? All right, so let's suppose we have this. Okay, this is similar to the example above. Let's rewrite it. And I see right away, once again, just like the example right above, that's our thing. Okay, that's the special case of the chain rule. It's missing a couple of things, right? The outside is almost the derivative of the inside. What am I missing? Good, I'm missing a 2. So I'll multiply by a 2 here and a 1/2 on the outside to compensate. Okay, what else am I missing? What should be right here in front? What number did I have to bring down in front and then subtract 1 from to get the -3? Yes, good, a -2. So I need a -2 here, and I'll compensate by dividing by 1 over -2 on the outside. Okay, now this is a perfect chain rule, the special case. Okay, so I've got the 1 over -2, the 1 over 2, which is 1 over negative, let's just make it -1/4. Okay, but otherwise, all of this came from finding the derivative of 1 plus x squared to the -2, and then plus c. All right, now let's check. You don't want to take my word for it. Let's check it. Okay, take the derivative of the answer. All right, so let's set the -1/4 aside. By the chain rule, the -2 comes down, subtract 1 from it, and then multiply by the derivative of the inside. The derivative of that constant is 0, okay? The negative and the negative make the whole thing positive. This 2 and this 2 give me 4, which will cancel with the 4 right here. And this will simplify then as x over the quantity 1 plus x squared to the third. And it checks out, okay? So be on the lookout, gang, for chain rules, all right? Especially the special case of the chain rule, all right? Maybe we'll do one more example. Let's do, I suppose we have the cosine of 3x, okay? Now, gang, if this was going to be a chain rule, it would be missing something, okay? What would it be missing? Yeah, it'd be missing a 3, huh? Right? It would be missing a 3. So maybe we write cosine of 3x multiply by 3 here, divide by 3 on the outside to keep it even, to compensate, okay? And then it looks like what we would get is 1/3. This is now a perfect, it's not the special case, all right? It's not our thing, right? It's not the special case of the chain rule. It is a chain rule where the outside is the derivative of the inside, though. Must have come from this. From our experiences, it must have come from this. Okay, let's check, just to be sure. Take the derivative of this result. Set the 1/3 aside. The derivative of the sine of 3x is the cosine of 3x, multiplied by the derivative of the inside function, which is a 3. The derivative of that constant is 0. Cancel the 3's to get the cosine of 3x, which is what we started with. Check.